used for seeding loose, dry snow and the firmer grains. So basically the first thing that we do is create a mesh sphere with the same overall size and location as the snowball that we want to create. And then we deform the snow with just a simple deformer with some simplex noise. Then we create the grains. We just randomly sample some particles within the snowball and then cull the points that are too close together, and we've got our positions of the centers. Then we randomly choose some radii for the grains. We make some little spheres, and again, add some simplex noise to create our final grain meshes. And then we pass the geometry into source npm snow, where we specify the initial parameters of the snow particles. And that basically is all there is to it to create the final snowballs. We just pass them into the solver from there. So here we've got the dynamics of an avalanche. We're basically simulating the snow falling down the mountain and the tents as well. The tents are down to the individual stakes and the little ropes holding them in. So basically, the tension in the ropes is what's holding those tents in place. And that's why the tents actually begin to collapse a little bit before the snow gets there, because they can sort of feel the elastic waves coming down. The parameters of the snow were tuned at a lower resolution. I created this debug visualization by making a Bifrost compound, which first post-processes the snow particles, adding colors to show the types of deformation and any internal cracking. The first second of this video is a pre-sim where the stakes of the tent are slowly pulled apart in order to add tension to the ropes so that the tent will stay up once gravity is turned on. The parameters in this particular sim were not used for the final version, as this snow was too cohesive. But I wanted to show the dynamics. In particular, the ground shifts underneath the tent and it gets torn apart a bit. The performance of this sim was excellent, at only about 2 minutes per frame, with 16.5 million particles simulated. The full snow volumes for rendering contained 285 million voxels. Snow particles have quite a bit more state than, say, fluid particles, as the material needs to remember how it's been deformed. So the full state is about 1.6 gigabytes on disk per frame. The entire rendered snow volume is actually smaller in bytes, at only 568 megabytes per frame, because it stores less data per voxel. Thank you, and I hope that you enjoy using our npm solver.
Hello everyone, I'm Jonah Friedman. I'm the product owner of Bifrost, and I'm here talking today about strands, instancing, and how that collides with visual programming. So I'm going to talk about the creation of this image right here, which I call a cable car. And yeah, this was for the brief, sorry. It's so the cables are all strands. So what are strands? The name of strands comes from soft-homage ice, and a strand's geometry is a geometry representing many curves. So kind of like a mesh is a geometry representing many polygons, a strands is an object representing many curves. And these can be procedurally generated in the Bifrost graph. And then they can be rendered in Arnold, in this case, as thick curves with a standard shader. And then I also have this variant of it, which is using instancing to generate chain links instead of using the strands to render with. And an animated version. And here's what strands look like in the Maya viewport. So strands have width and color, and these things display in the viewport, which is really important to be able to see what you're doing. And down there at the bottom is the real node graph that generated those images. So the ones on the blue backdrop are the ones I'm going to be talking about, and those are the ones that actually created this image, really. The purple ones are the rendering setup, and the ones that are not on backdrops are kind of plumbing. And all of these components are very general building block components. They're not like so specialized for this particular setup. And they're also all available today. So I'm hoping that by describing these components and what they are and how they're built, I can give you a really good sense of what it's like to work in the Bifrost graph and use a visual programming system to generate content. So what I kind of set out to do was explore flow lines as art. And we have a node called the volume scope. And volume scope has a day job that's visualizing simulations. It's moonlighting as an artistic tool here, but that's its day job. And what I'm doing here is I'm making a flow line from every point on a plane, and then I'm using that to see a slice through my arrow simulation to see the exact flow of all the velocities through it. And the reason I wanted to explore flow lines as art was because fluid simulations produce really organic and dynamic shapes that are really interesting. And the arrow sims are also zero divergence, which means that no two flow lines can collide. And that's a really useful property to have if you're trying to fill a volume with really complex geometry. Kind of get that for free. So volume scope is the node that makes flow lines, and it's implemented entirely in the graph as a compound. And a compound is a node in the Bifrost graph that's made of other nodes. So this little graph that's shown here is kind of like the core inside of volume scope. And that's the part of the graph that's actually sampling the volume in order to do this. And I have a visualization of this. So basically we have this point cloud here, that little grid in front of the car. The white points represent the points that are being sampled. The little green vectors are the velocities. And I said this was the inside of the loop. So if I play this animation, each frame of this animation is actually one iteration through this loop. So what we're doing here is, every single time it advances, it samples the velocities, moves forward along the velocities, adds another point cloud to the array, and then loops like that. Afterward, the data is rearranged into strands, but that's basically how it works. And volume scope is a diagnostic tool, and this is the diagnostic of a diagnostic tool that I made in the graph. Second node is a simple one. It sets strand size profile. So this is a compound, also made of nodes, and it's setting the sizes of these strands using an F curve. That curve there has them small at the beginning, big in the middle, and then small at the end with kind of a ease out type of fall off. And that produces like really nice looking tapered ends. In the graph, it's really simple. It's just mapping a 0 to 1 value along the strand onto an F curve and then setting the size with it. Next one is update strand basis. This is kind of a basic building block and maybe a little bit abstract, but what this does is it essentially generates orientations along the strand by walking down the strand from the start. So this is implemented as two nested loops here, and it's also, I have a visualization of it as well, so you can see that the normals, binormals, and tangents together are forming basically an axis that we can use for the next step, which is creating strands around strands. So also a compound, and this is actually really easy to do, provided that you have basis vectors already. If you don't have basis vectors already, then you should really just go back and make basis vectors. There's no substitute. But so you have your basis vectors, you take your input strands, you make copies of them, you deform each of the copies into a helix with a different offset, you merge them back together, and you're done. So it's not terribly complicated at all. And you put all this together, and you get this image. One thing to call attention to is that the coils of the cables are not all equal density. Some of them are kind of spread out, some of them are denser. I left this in on purpose. This is actually a side effect of the velocity of the field being different. Where the velocity is slow, the coils are tighter. And I like the look, so I kept it. But that kind of thing is going to be a problem if you want to make chains, right? Because you need everything to be very, very evenly spaced. So this is rendered using instancing, another feature of Bifrost. So what is instancing? Instancing are render time copies of geometry. This is how you get to enormous complexity in scenes by generating lots and lots of instances. And Bifrost instancing is what's known as point cloud instancing, which means that we have one geometry representing many instances, just like we have one geometry representing many curves as strands. This is one geometry representing many instances. So pictured here, I'm using scattered points in order to generate instancing, but for the example of the cable car, we're going to use chains instead. We're going to use the strands instead as the source of the instancing. So we're going to produce one instance per segment of our chain, right? Or one instance per segment of our strands. So we really need them to be evenly spaced. And as we talked about before, because the velocities are not the same, they're not evenly spaced. So we have this node in the graph that resamples the strands. And that does this, roughly speaking, by computing the length along the strand, and then iterating the new strands and the old strands at the same time in order to create a new strands object where it's totally evenly spaced. And that's not a trivial algorithm. In programming, this is called a double iterator. And I'm showing the node graph for it here, which goes 5 levels deep. I'm not going to go into it in too much detail, but what I want to point out here is that this is not a trivial algorithm, and this node graph is not spaghetti, right? Like every level of this is fairly readable. This is not the kind of thing that you do just to kind of prove that you can do it. This is actually a practical way of doing this kind of thing in Bifrost. Because what this is doing is iterating the new strands and the old strands at the same time, depending on how long each segment of each are. After that, our instances are going to need orientations. We already have basis vectors, so I'm just going to take my basis vectors and generate orientations from them, and I'll rotate every other chain link by 90 degrees. There's a node graph that does that. It's kind of an ad hoc node for chains in particular. And then I'm going to add instances. And it's really easy in Bifrost. Any point-based geometry, you just add instances to it, and you get an instance at each vertex. Usually it's point clouds, but in this case it's strands. I just plug the strands directly in, put in a chain link, and I get my instances of chains. We can instance some different things as well. We can instance Bifrost geometry, which is what we're doing. That's the chain link. We can also select from a lot of different instance shapes, so we can have a powerful instance selection mechanism. We can instance Bifrost compounds themselves. I don't have time to talk about that, but that's super interesting. You can generate huge numbers of procedurals at the same time. And we can instance Arnold render archives. Those are ASPOS, of course. And yeah, I'm going to end on this image here. I switch things around a little bit. I have cars floating around chains instead of chains floating around cars. But this is the full resolution car that's rendering here as an Arnold AS file, and it's fine. And thank you very much.
Thanks, Jonah. Thanks, Jonah. Hi, I'm Todd Akita on the Mill. I'm an effects supervisor out of the New York office. At the Mill, we create content and experiences from 5 offices: London, New York, LA, Chicago, and Bangalore. And what I'm going to be sharing with you today is some of the work of my colleagues and some of the work that we've been doing with the Bifrost team at Autodesk. In the effects department, our primary focus is the simulation of natural phenomena: smoke, fire, water, destruction, that kind of thing. We do not have a dedicated CFX department, so also additionally, performance-driven simulations also fall under our purview, so cloth, fur, feathers, flesh, that kind of thing.